So this video refers to Lecture 4, Moments, and specifically is looking at scalar and vector techniques to solve questions regarding moments. So the first one we're going to look at relates to the question beginning on slide 14 with a 100 Newton force applied to a frame. The diagram looking something similar to the one you've got in front of you. Relatively simple. To start with, we just start to resolve the force into x and into y. So in the x direction we're going to have 4/5 of 100, and in the y direction we're going to have 3/5 of 100. Hopefully that bit you remember from the forces lectures. Then our moments, if we're calling anti-clockwise positive as we normally do, then our moment about point O is going to be, well, if we think about the x component first, the x component is going to be going that way. It's going to be trying to turn the frame clockwise. So if it's trying to turn the frame clockwise, it's negative 4/5. Where's the perpendicular distance for that? Well, it's going to be this distance here, because that's the perpendicular distance from point O. So it's going to be 4/5 of 100, sorry I missed that, times 2 meters. In the y direction, we've got a similar thing. We've got the y component which is acting this way. It's going to be this perpendicular distance, so 5 meters. So we're going, and it's also turning clockwise. So we're going to have minus 3/5 of 100. It's going to be times 5 meters. So both of those negative signs are due to the direction that the moment is acting, not due to the direction that the forces are acting. But the solution for that will come out at minus 460 Newton meters. Minus because it's going the opposite direction to the direction we call positive. So the notes also say 460 Newton meters clockwise. So that's the first example solved. I'll just pause this and sketch the next example, then I'll explain how to do it. So this vector question for moments, we've got a point which is labelled in the diagram as O here. We're looking for the moment about it, and we've got two forces, force 1 and force 2. Obviously we haven't done anything with two forces, so there are two ways of doing it. We could either find the separate moment effects of each force and then add them together, or we could find the resultant force, because they're acting at the same point, the resultant force, the position vector, and use the cross product. So we're going to do it that way because it's slightly easier. So the resultant force, you should remember from last time how we did that. So it will just be the I component, so 100 minus 200, so minus 100 I, minus 120 plus 250, so plus 130 J, and then 75 plus 100, so plus 175 K. So that's our resultant force. Our position of how we get from O to A, this being point A here, apologies I didn't label it. So how do we get from O to A? Now I've drawn my coordinate axes. I've just drawn which directions they're going on the top of the page, just so it was a bit clearer what was happening in the diagram. But in the x direction, I'm travelling 4 meters, so 4I. In the y direction, I'm travelling 5J, and in the z direction, I'm travelling 3K, and they're all positive. So now all I have to do is find, is put these into a matrix and then cross them out. So moment as a vector is going to be I, J, K. It's going to be R crossed with F, so it's 4, 153, minus 100, 130, 175. So I'm going to move to the next page and then write that up again and then cross it out and show you how to get a solution. So this is the same matrix as before, just that should say 175, that bottom. In fact, let's rewrite it for you. 175. So to find our I component, we're going to do 5 times 175 minus 3 times 130 I. We're going to do for the j component 4 times 175 minus 3 times minus 100 j. Because it's j, that's automatically a minus there, plus for the k component 4 times 130 minus 5 times minus 100 k. So if I put those three components separately into the calculator, I'm going to get 485i minus 1000 j plus 1020 k. That's how you would solve a three-dimensional problem using vectors and using the cross product. There are now 2 questions in the lecture for you to have a go at. One of them, the first one, the scalar one, if you do look at the solution in the lecture, there are some mistakes. I'll try not to make those mistakes in the video. But on the solution page, the second slide, so slide 20, there are a couple of typos. If you pause the video now and then come back to this video when you've had a go at your questions, I'll show you how to solve them. Okay, so you should now have had a go at least the first group problem solving task beginning on slide 19 of lecture 4. It's the one with the 100 Newton force being applied to the hammer. So it's a scalar problem. It looks something similar to what I've given you here, apart from it's got one more dimension in it that I've missed, and that I've drawn quite badly. But that dimension there should be 125 millimeters. Sorry about that. So that's the diagram you've got, something similar to that. So the first thing you'd do is you'd find your forces in the x and in the y. Force in the x is going to be 100 cos 30, and in the y will be 100 sine 30. So my force in the x will be acting that way. So my perpendicular distance from A will be that one. So my moment about point A, calling anti-clockwise positive, is going to equal, well, the x component is going to be trying to turn it clockwise, so minus 100 cos 30 times 415. You can leave it in millimetres if you want to. My y component is going to be trying to turn it, but it's also going to be trying to turn it clockwise. So it's going to be minus 100 sine 30 times 125 millimetres. So if I put those 2 numbers into my calculator, I'm going to get minus 45,221 Newton millimetres, or 45,221 Newton millimetres clockwise. So that's example 1 done. That is slightly different to the solution on the slide, which uses the wrong angle. The second angle is marked down as 20 and it should be 30 degrees. So group problem number 2, which begins on slide 21. Again, I'll sketch it. if you pause the video, have a go, and then start the video again when you're ready to see the solution. Okay, so this is group problem solving exercise number 2 from lecture 4 on moments, and is looking at a vector solution, making it slightly more tricky than the examples because it's bringing in some of the things you should have done from the forces lecture as well. So you need to find that force, that 80 Newton force, which is all the way down here as a Cartesian vector. So let's start with that. Our force, and again this is resolving it into three directions. Well, the I component, to find the I component will be acting in this direction, in the same in the same direction as the 250mm bar is stretching that final bar. To the X component, we're going to have to do some intermediate steps. So we're going to have to raise that 80 newtons into this plane, and then we're going to have to resolve it along the red line, the x-axis. So to raise the 80 newtons onto that green line, we're going to have to do 80 cosine 30, and to then turn the green line so that it's along the new red line, along the 250mm bar, we're then also going to have to do sine 40 to make it in the I direction. And similarly for the J component, we're going to have 80 cos 30 to raise it to the green line, and then cos 40, should be an S, sorry, to put it into the J direction. And both of those are positive. It's also going downwards, so there's going to be a negative Z component, and that's much simpler because that's just taking this bit straight down here. So it's just going to be 80 sine 30, and that's in the K direction. And if we put those into a calculator, we're going to get, no we're not, sorry, we're going to get 44.53i, we're going to get plus 53.07j, and we're going to get minus 40k. So that's our F, our force. It's a Cartesian vector. We also need to know how we get from A to C. Let's label this point A, and that point there where the force starts, point C. To get from A to C, in the X direction, we travel 300mm and another 250mm. So in metres, 0.55. You can leave it in millimetres if you want and have 550, that's fine. In the J direction, we're travelling 400mm from A to B. In the diagram, it's labelled B just here. So 400mm or 0.4J. And in the Z direction, we're moving down 200mm or minus 0.2K. So I'm going to move to the next slide so that I can start to solve that. Translate it into a matrix. So my next page, we're going to have I, J, and K. We're going to have 0.55, 0.4, 0.2, and that should be minus 0.2, 44.53, 53.07, and minus 40. That's my matrix. That's my R crossed with my F. If I then start to work out my my three I, J and K components of my moment as a vector about point A, that's going to be, for the I component, 0.4 times minus 40 minus 0.2 times 53.07 I. it's going to be minus for the j 0.55 times minus 40 minus 0.2 times 44.53 j, apologies that's run all the way down there, and for the k it's going to be plus 0.55 times 53.07 minus 0.4 times 44.53 k. So my final moment should equal minus 5.39i plus 13.1 j plus 11.4 k. So that's your final solution to the cross product, and that ends the examples that introduce the cross product. You've now looked at examples for solving simple moments in both scalar and vector form. So if you follow on to the next series of videos for lecture 4, I'll go on to explain how we can use particularly the vector form in more detail.